In the mid-1940s, the Pennsylvania Railroad built one of the most powerful steam locomotives ever put on rails. It could generate 6,900 horsepower at the drawbar, numbers that made even the biggest articulated mallets look modest. It didn't suffer from wheel slip. It didn't lack tractive effort. Instead, it kept destroying itself from the inside. This is the story of the PRR S2, a locomotive that proved raw power means nothing if your bearings can't survive it. The Pennsylvania Railroad wasn't just another railroad. By the 1940s, it was the largest railroad in the world by traffic volume and revenue, moving more tonnage and passengers than any competitor. Its engineering culture was built on precision, efficiency, and an almost obsessive willingness to fund experiments that other railroads wouldn't touch. PRR had its own test plant in Altoona, Pennsylvania, a facility that could measure locomotive performance with scientific rigor. This wasn't a railroad that guessed. It measured, tested, and optimized. PRR's engineers had already pushed steam locomotive design further than most thought possible. The T1 duplex, with its divided drive system, represented an attempt to eliminate the reciprocating forces that limited speed and efficiency in conventional designs. But even the T1 had limitations. The reciprocating motion of pistons, side rods, and valve gear created hammer blow, a vertical force that pounded the rails and wore out track infrastructure. At high speeds, this became a serious problem. Steam turbines offered a compelling alternative. Unlike piston engines, turbines operated on continuous rotary motion. There was no hammer blow, no violent reciprocation, no need for counterweights that limited balance and speed. Turbines were already proven technology in marine applications and stationary power plants, where they delivered smooth, efficient power at high outputs. The question wasn't whether turbines worked. It was whether they could work on a railroad. The timing mattered. This was wartime America, and the country was drowning in cheap coal while worrying about oil security. Diesel-electric locomotives were still relatively new, unproven in heavy mainline service, and dependent on petroleum. Electrification was prohibitively expensive outside the densest corridors. If turbines could deliver diesel-like efficiency while burning coal, PRR would have a solution that fit America's resource base. The logic was sound. The execution would prove otherwise. The PRR wasn't alone in this thinking. The Chesapeake and Ohio Railroad and the Norfolk and Western Railway were also experimenting with turbine locomotives during this period, though their approaches differed. But PRR went furthest. In 1944, they ordered their first direct-drive steam turbine locomotive from Baldwin Locomotive Works in Westinghouse, the S2. It entered service in 1944 as a 6-86, meaning 6 leading wheels, 8 driving wheels, and 6 trailing wheels. It was enormous, experimental, and represented PRR's bet that turbines could replace reciprocating steam entirely. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. Here's where most discussions of the S2 go wrong. The locomotive is often described as turbine electric, suggesting it used an electric transmission like a diesel electric. That's incorrect. The S2 was a direct-drive steam turbine locomotive with mechanical reduction gearing. This distinction matters because it explains why the bearings became the failure point. The turbine itself sat in the middle of the locomotive, mounted horizontally and fed by steam from a massive boiler. Unlike a piston engine that converts linear motion into rotation, a turbine extracts energy directly from high-velocity steam flowing across bladed wheels. The steam entered at high pressure, expanded through multiple turbine stages, and exhausted at low pressure. The process was efficient, at least in theory. The turbine could spin at extremely high speeds, far higher than any piston engine. The problem was translating that speed into usable wheel rotation. Railroad wheels don't turn at 10,000 or 15,000 RPM. They turn at a few hundred RPM at most. That meant the S2 needed massive reduction gearing to drop the turbine's rotational speed down to something the driving wheels could use. This wasn't a simple gear pair. It was a complex reduction system with multiple stages, each stage multiplying torque while decreasing speed. And every gear stage required bearings to handle the load. Bearings became the weak link. In a conventional steam locomotive, bearings on driving axles deal with relatively modest rotational speeds and intermittent loading from the reciprocating mechanism. In the S2, Bearings in the reduction gear train had to handle continuous high speed, rotation under sustained load. Heat became an immediate problem. So did lubrication. So did metal fatigue. Turbines also behave differently under load than piston engines. A piston engine delivers discrete power strokes, bursts of force that drive the wheels forward. A turbine delivers continuous smooth power. That sounds like an advantage, and in some ways, it was. The S2 was incredibly smooth to ride. But continuous power meant continuous thermal and mechanical stress on every component in the drivetrain. There was no rest period, no momentary relief between strokes. Everything ran hot, all the time. The S2 was rated at 6,900 horsepower at the drawbar, making it one of the most powerful single-unit locomotives ever built. But power means nothing if the machine can't deliver it reliably. The turbine worked. The boiler worked. The reduction gears worked, at least for a while. The bearings did not. Bearings seem simple. They're just metal surfaces rolling or sliding against each other, separated by a thin film of oil. But at high speeds and high loads, bearings become precision instruments that operate at the edge of material science. The S2's bearings had to endure conditions that would have seemed unreasonable even in industrial applications. First, there was rotational speed. The input shaft from the turbine was spinning at speeds far higher than anything in a conventional locomotive. Even after the first stage of reduction, shaft speeds were extreme. High speed means high surface velocity at the bearing interface, which generates heat. Heat breaks down lubricating oil, reducing its viscosity and compromising the oil film that prevents metal-to-metal contact. Second, there was thermal load. The turbine itself generated enormous heat, and that heat radiated throughout the drivetrain. Bearings closest to the turbine operated in an environment that was already thermally stressed before they even began turning. Add the frictional heat from high-speed rotation, and you have a situation where oil temperatures could spike beyond their design limits. Third, there was variable torque. Railroads don't operate at constant load. The S2 might be pulling a heavy freight train up a grade, then coasting downhill, then accelerating out of a station stop. Every change in throttle position, every grade transition, every curve introduced load variations that turbines handle poorly. Sudden increases in torque could momentarily overload bearings before lubrication could adjust. Sudden decreases left bearings spinning with reduced oil pressure, inviting contamination and film breakdown. The oil itself was a problem. This was the 1940s. Modern synthetic lubricants didn't exist. High-temperature bearing oils were primitive by today's standards. PRR used the best oils available, but best available wasn't good enough. At sustained high temperatures, the oil would thermally degrade, forming varnish and sludge that clogged oil passages and reduced cooling efficiency. Contamination from steam leaks, metal particles from gear wear, and debris from the locomotive's environment all degraded lubrication further. When a bearing begins to fail, it fails quickly. The oil film breaks down. Metal surfaces make contact. Friction generates more heat. The bearing begins to seize. In the S2, a seized bearing could destroy the entire reduction gear train within minutes. The turbine itself could survive. It was robust, but the gearing couldn't. A catastrophic bearing failure meant tearing down the entire drivetrain, replacing gears, shafts, and bearings, and hoping the next set would last longer. During testing and early operational service, bearing inspections and replacements occurred so frequently that maintenance crews joked the locomotive spent more time in the shop than on the road. The every 500 miles figure wasn't a scheduled maintenance interval. It was an observed operational reality. The S2 simply could not complete long runs without bearing trouble. Some reports suggest it could handle short, high-speed passenger runs reasonably well, but sustained heavy freight service at variable speeds proved impossible. PRR tried everything. They tested different bearing materials, bronze, babbitt, hardened steel. They experimented with oil formulations, additives, and cooling systems. They tried limiting operational speeds and loads to reduce thermal stress. Nothing worked consistently. Each fix introduced new complications. Hardened bearings lasted longer, but were more prone to catastrophic failure when they did give out. Better oils helped, but only marginally. Operational restrictions defeated the entire purpose of building a high-power locomotive in the first place. The problem wasn't fixable within the material, science, and lubrication technology of the 1940s. Modern turbines use advanced bearing designs, synthetic oils, and active cooling systems that simply didn't exist when the S2 was built. PRR had built a machine that required technology from the future. The S2's bearing problems weren't just bad luck or poor engineering. They were a symptom of a fundamental mismatch between turbine characteristics and railroad operating conditions. Turbines are designed for steady-state operation. In a power plant, a turbine spins at constant speed under constant load, generating electricity for the grid. In a ship, a turbine drives a propeller through water at relatively constant RPM. Both environments are controlled, predictable, and optimized for continuous operation. Railroads are none of those things. A freight locomotive climbing a mountain grade experiences constantly changing load as the train snakes through curves, encounters grade transitions, and responds to throttle adjustments. Even on flat track, variations in rail conditions, joints, curves, switches introduce momentary load spikes. Passenger service is worse. Stations require acceleration and braking. Schedules demand speed. Changes. Every throttle movement is a transient event that turbines handle poorly. Turbines are efficient at design load. Move away from that load, either higher or lower, and efficiency drops. But railroads rarely operate at design load. A locomotive might be working hard on a grade, then coasting downhill with minimal load, then accelerating again. Piston engines tolerate this variation reasonably well because their power delivery is inherently transient. Each stroke is a discrete event, and the engine naturally adapts to changing conditions. Turbines don't adapt. They fight back. Compare the railroad environment to marine applications, where turbines thrived. A ship's turbine operates at near constant RPM, driving a propeller through a fluid medium that provides smooth, predictable resistance. Load changes happen slowly, over minutes rather than seconds. Cooling is abundant. Seawater flows continuously through heat exchangers. The entire system is designed for steadiness. The S2 had none of these advantages. Even the Norfolk and Western's John Henry, a turbine electric locomotive built in 1954, failed for similar reasons despite using electric transmission to buffer the turbine from load variations. The problem wasn't just mechanical, it was operational. Railroads are environments of constant disruption, and turbines demand order that railroads cannot provide. PRR didn't give up easily. The S2 underwent extensive testing at Altoona and in road service, and engineers tried every conceivable workaround to make the locomotive viable. Different oils were tested, some with higher viscosity ratings, others with temperature stabilizers. Bearing materials were swapped out repeatedly. Gear ratios were adjusted to reduce shaft speeds and thermal loading. Operational protocols were implemented to limit the locomotive's use to certain speed ranges and train types. None of it worked reliably enough to justify continued operation. Each fix created new problems. Higher viscosity oils reduced heat buildup, but increased drag, cutting efficiency. Softer bearing materials wore out faster. Harder materials lasted longer, but failed catastrophically when they did give out. Operational restrictions meant the locomotive couldn't do the work it was designed for, defeating the entire purpose of building such a powerful machine. Crew confidence collapsed. Engineers and firemen didn't trust the S2. They knew it could fail suddenly and violently. A seized bearing could happen at any time, leaving them stranded with a dead locomotive and a heavy train. Stories circulated about breakdowns, emergency repairs, and delays. Word spread among operating crews that the S2 was unreliable. In railroad culture, that's a death sentence. Locomotives live or die by the trust crews place in them. By 1949, PRR had seen enough. The S2 was withdrawn from service and eventually scrapped. It had proven that steam turbines, no matter how theoretically superior, could not survive in railroad service with 1940s technology. The fundamental problems, bearings, lubrication, thermal management, were not engineering mistakes. They were technological limits. The PRR S2 failed, but it failed instructively. It demonstrated that raw power and theoretical efficiency mean nothing if the machine can't deliver them reliably in real-world conditions. The turbine worked. The concept worked. The materials and technology of the 1940s did not. Diesel-electric locomotives won because they avoided the S2's problems entirely. Diesel engines operate at much lower rotational speeds than turbines, typically 500 to 1,000 RPM, well within the capability of contemporary bearing and lubrication technology. Electric transmission buffers the prime mover from wheel load variations, allowing the diesel engine to run at optimal speed regardless of train speed or load. When a diesel component fails, it fails gracefully. One traction motor, one generator bearing, not catastrophically. Diesels were maintainable with existing shop infrastructure and tools. The S2 was not. The S2 also revealed the limits of PRR's engineering culture. PRR was willing to push boundaries, fund experiments, and test radical ideas. But pushing boundaries requires knowing where the boundaries are. In the 1940s, bearing and lubrication technology simply wasn't ready for high-speed, high-load turbine service in a variable, hostile environment like railroad operation. PRR learned this the hard way. The lessons from the S2 weren't wasted. Modern gas turbine locomotives, like Union Pacific's later experiments in the 1950s and 1960s, avoided direct drive mechanical transmissions entirely, opting for turbine electric designs that insulated the turbine from the brutal realities of railroad operation. Even those eventually failed, not because of bearings, but because diesels were cheaper, simpler, and more fuel efficient. The PRR S2 didn't fail because it lacked power. It didn't fail because the turbine was a bad idea. It failed because railroads punish complexity and forgive simplicity. It failed because it demanded precision from an industry built on brute force and reliability. It failed because 1940s technology couldn't deliver what the design required. And in doing so, it taught the Pennsylvania Railroad and the entire industry that sometimes the future arrives too early.